Hello, dear ones. I believe you're all doing well. You're all welcome to today's lecture. In our previous lectures, we looked at the effects of load changes on the synchronous motors, keeping the field excitation constant. And then we also looked at the second scenario, that's keeping the load constant and varying the field excitation, the effects on the synchronous motors. Okay, today we are going to focus on another topic, that's power factor corrections. Okay, we made mention that synchronous motors have the ability to operate in both lagging and leading power factor, and thereby can be used to improve power factor of a power system. Okay, so now we are going to solve one example and see how synchronous machines or motors are used to improve power factor in a power system or in an industry. Okay, so assuming that a load contains a synchronous motor whose power can be adjusted, okay, in addition to motors of other types that can be an induction motor or whatever. Okay, so what does the ability to set the power factor of one of the loads do for the power factor, the power system? Okay, so that's what basically we are going to do. So we have a question that we are going to look. So the question says that let's consider a large power system operating at 480 volts, and then these are the loads connected to this particular power system. Okay, so first load is an induction motor consuming 100 kilowatts power at 0.78 power factor lagging. The second load is an induction motor, once again consuming a power of 200 kilowatts at a power factor of 0.8 lagging. And then the third load is a synchronous motor whose real power consumption is 150 kilowatts. Okay, so this is the power network that we have over here. Okay, with the various loads connected to it, and then each load and its ratings. The first one, they say is an induction motor with a real power of 100 kilowatts and a power factor of 0.78 lagging, and then another motor, also an induction motor with a real power of 200 kilowatts and a power factor of 0.8 power factor lagging. Then we have a third load, that's a synchronous motor with a real power of 150 kilowatts. For the power factor, you look at it. Okay, so the question says that if the synchronous motor is adjusted to a 0.85 power factor lagging, what is its line current? So at this particular scenario, we are operating the synchronous motor at a power factor of 0.85 lagging. So they want us to find the line current. So the current that we will measure on the line. So they want us to find this particular IL. But if you want to measure this particular current, okay, this system will be seeing this load as one but not as three individual loads. Okay, so we know that power is equal to root 3 VL cos theta. So if you want the total power, because this particular infinite bars will be seeing this as one power or one load. So if you want the total load or power consumed by the load, then we have to find the total power of all the three loads. So the total power will be equal to root 3 VL cos theta t. Okay, so we can easily find this particular total power because we know the real power of all the motors. So that one we can get it from P1 plus P2 plus P3, which we can do a simple algebraic summation of the three. So that will give us a 450 kilowatts. Okay, what about this theta t, or the total theta? Okay, that represents the overall power factor of our power system. We can't just do algebraic summation of all the three. That will be suicidal. Okay, there's a way that we can find the total theta of the system. Okay, so what you do is we are going to use the power triangle that we all know from our applied electricity AC fundamentals. We know that the power triangle, we have the hypotenuse to be the apparent power, the opposite to be our reactive power, and then the adjacent, which happens to be our real power. So if you know the total real power, total reactive power, we can easily find our total theta. Okay, but in the question we all know that we were not given our reactive power, so it means we have to be able to calculate the reactive power of the first motor, reactive power of second motor, reactive power of the third motor. Then when we finish, we sum all the three, then we get the total reactive power. Then with that, we can come and calculate for our total theta, so that we can solve the question. Because the question says that we should find IL. So if you know the total theta, we can make IL the subject and then find our IL. Okay, so let's see how we are going to find the reactive power of all the loads. So we begin with the first load, that's a motor 1. Okay, so if you're able to, since we know the real power of the first load, and we know the power factor, once again we can use the same power triangle to find our, we know that the power factor is what, 0.78 lagging. So we can find theta. We know cos theta is the power factor, so cos theta is equal to 0.78. So we can make theta the subject. So cos inverse of 0.78 will give us 38.74 degrees. Using trick or the SOHCAHTOA, we can find our Q1, or the reactive power of the first motor. So Q1 will be equal to 100 kilowatt tan 38.74, and I believe you know why we are using tan. We are using the TOA. So if you make theta Q the subject, it will be 100 kilowatt tan the theta, and we will get Q1 to be 80.23 kVAR. That's a kilovar. Okay, that's a unit for reactive power, the kilovar. All right, so that is for the first load, and then we go to the second load and find the reactive power of the second load also. The second load too has its power factor to be 0.8 lagging. So once again, we have to find our theta. So cos theta is equal to 0.8. Okay, so making theta the subject to be cos inverse of 0.8, which will give us 36.87 degrees. So knowing the theta, this angle, we can find our Q2 using the TOA, or the SOHCAHTOA. We will use the TOA. Okay, so making our Q2 the subject, it will be 200, or the real power, this side real power, 200 kilowatt tan, the angle 36.87, and once again we will get our Q2 to be 150 kilovar, or kVAR. That is for the second load. And then the third load, okay, we take the case 1. The case 1 in the question says that the synchronous motor is operating at a power factor of 0.85 lagging. So we consider the lagging scenario to find the reactive power under that condition. So the reactive power under that condition, 0.85 lagging. If once again we find this theta, we know that theta is equal to the power factor. So cos theta is equal to 0.85. So cos inverse of 0.85 will give us our theta, and we have 31.79 degrees. So we can go ahead to find our the reactive power Q3. So Q3 will be 150 kilowatts tan 31.79, and with that we will get our reactive power for the Q3. Okay, so now we can sum up all the three reactive powers and we'll get our common, or our total reactive power. Okay, so we know that our total reactive power will be equal to Q1 plus Q2 plus Q3, and we can get a total reactive power. Then if you get that, then you come and find our total theta. Here we were using the individual theta for the individual loads, each load. Okay, now getting the total real power, the total reactive power, if you use that one to calculate for our theta, then that will be the total theta. Okay, that we can substitute into this particular formula and find our IL. All right, and we know that if you want theta TOA, it will be tan inverse of the real power, the reactive power, total reactive power over total real power will give us our total theta. So let's see how we did that in our slice. So that's the same method that we use, but just that I use the diagram, the power triangle, to explain it to you. So the first scenario, finding the Q1 is tan P1 tan theta, which is 100 tan into bracket. We know that theta is the power factor. Cos inverse of the power factor will give us the theta. So that's why they brought the cos inverse of power factor here to get the theta. And we have 80.2 kilovar. Okay. the same thing that was done to Q2 also, and we had 150 kiloVAR. And then the Q3, and considering the case 1 that's operating at a power factor lagging, we had it to be 93 kiloVAR. Okay, so now we can find our total power. Okay, and we had the total power to be 150. That's the real power of the load 1, load 2, load 3, and we had 450 in our previous slide that I just showed you. And then the reactive power, to when we sum up the reactive power of the 3 loads, we had a total reactive power to be 323.2 kiloVAR. All right, so now knowing this, okay, we can substitute everything into the formula, and then we calculate for our theta. Okay, so we can calculate for the theta, or we can calculate for the power factor also. So if we are to use the other formula that I showed you, if we are to use this one, we will get the total theta. So we can just substitute in this formula straightforward. So we know the theta. But in the slide, what I showed you, we calculated for the cos theta. And then that one too, you can also use it to solve. But I always prefer calculating for theta and just substituting this particular formula. It will make the work so simple and easy for you. Okay, so take note of that. So now we know we know the total P, we know the total Q. We know that the tan inverse of Q over P will give us theta. Okay, so this particular value will give us theta, and we know that the power factor is what? Cos theta. So we can put theta here and calculate for the cos theta alone, this particular cos theta, so that we will not come and put the theta value, but we will come and replace it with the total cos theta value. As I said previously, we can calculate for only this theta by considering only this part of it. Okay, to calculate for only theta, in that case we come and substitute only this theta. But here we calculated for the entire cos theta to get a power factor of 0.812. So we come and replace it by this particular value, and each of them you get the same answer. So now the line current, which is equal to the total real power over root 3 multiplied by the line voltage cos theta, and we know the line voltage was given to us by 480. Okay, root 3 multiplied by cos theta. Here we calculate for the cos theta straightforward. So we had it 0.812 power factor lagging, and in the total power, real power too, we had it to be 450 kilowatts, so 450,000 watts. And if we compute this, we are going to get our line current under the first scenario to be 667 amps. Okay, so that is for the first part of the question. Okay, so the second part of the question says that if the synchronous motor is adjusted to 0.85 power factor leading, this time around leading, what is the line current? Okay, so now this power factor is 0.85 leading, the other one was lagging. So what would be the new power factor? I mean the new line current at this particular scenario. So once again, we'll go through the calculations again to find the Q1, Q2, and Q3. And since the induction motor, motor 1 and motor 2 values hasn't changed, it means that the reactive power of the two are still going to maintain the same. The only change will be for the Q3. Okay, the synchronous motor, because we have changed the excitation. So we need to calculate for a new Q3. Okay, and we know that when a synchronous motor is operating at a power factor leading, it rather generates reactive power. Okay, when it's lagging, it consumes reactive power. When it's leading, it's generating reactive power. And when I say it's generating reactive power, it means that it's consuming a negative reactive power. We made mention of this in our previous lecture. Okay, so take note of that. When it is consuming, it's consuming a positive reactive power. When it is generating under leading condition, when it's generating, it's consuming a negative reactive power. So take note of that. So in this case, in the second case, the Q3 that we are going to get should be a negative reactive power. Okay, so once again, P3 equal to tan theta, which is 150 tan theta into bracket negative, the negative because of the leading, okay, the leading power factor. Okay, so in that case, we are going to have 93 kiloVAR, negative 93 kiloVAR. Since the power factor is 0.8 lagging and the other one was 0.8 leading, you can see that we have the same 93, 93, just that this one is positive and this one is what? Negative. Take note of that. Okay, so once again, we find our P total, and the P total never changes. It remains 450 kilowatts. But the Q total, now we have Q1 plus Q2 plus Q3. We had a Q1 to be 80.2, Q2 to be 150. Now our Q3 is negative 93, so it will be minus 93. So we have our total reactive power to be 137.2 kilowatt. So take note of that. The only changes came as a result of the leading, and with the leading, it is going to have effect on the Q3. Okay, that's why we had this particular value. So we go ahead now, knowing the total Q and the total P, we can go ahead and find our theta. Okay, so finding our theta, we know that our theta or cos theta is equal to cos into bracket tan inverse of theta, Q over P. So tan inverse of Q over P, this particular side will give us the theta, only the theta. Okay, so cos of it will give us the power factor. All right, I believe you know what we are talking about. Okay, so if you compute with the new values, you are going to get a power factor of 0.957 lagging. Okay, so this is our new power factor if the synchronous machine is allowed to operate at a power factor leading. So now let's compare the two power factors. So here you can see that the overall power factor of the system is 0.957 lagging. The other one, it was 0.812. So you can see if we adjust the power factor of the synchronous motor, we can see that the power factor of the entire system, the overall power factor, has improved from 0.812 to 0.957 lagging. So now let's see what we can do to get our line current, because the question said that we should find a line current. And once again, we will make the line current subject, so the P total will be equal to over root 3 multiplied by the VL cos theta, and we have the cos theta to be 0.957 lagging. So if we substitute, we are going to get a current of 566 amps. So we can also make another deduction here. We can see that at this scenario, we are having a current 566 amps. The previous one, we are having 667. So if the machine is operating at a lagging power factor, which resulted in this particular overall power factor, we are having a higher line current than when the power factor was improved. We are having a lesser line current, and you know the effect of line current on the power system. Higher line current means that higher losses, the I square R losses, and lower line current means that lower losses. So if you allow the machine to operate in improved power factor, you have less losses. But a reduced power factor, then, or a poor power factor, you have higher losses. So let's see what the third part of the question says we should find, because that one best explains the last point that I just made. So now the question says that we should assume that the line losses are PLL, that's the line power losses, okay, to be 3 multiplied by IL square RL. Okay, so how do these losses compare in the two cases? Okay, so they want us to find the power losses in the two scenarios. So we first find the power losses under the first scenario, the power loss under the second scenario, and we are fortunate they give us a formula. So it's a matter of substituting our values, and then we'll move on. So we know that in the first case, we had our IL to be 667 amps. Okay, that's the first scenario. We had the IL to be 667 amps. Okay, so you substitute that particular value here. Okay, so 667 amps square multiplied by 3 multiplied by RL. Take note, we are not giving RL value. So if you do that calculation, you have 1344700 RL. That is for the power losses. Okay, since we're not giving RL, just maintain the RL. Okay, and then for the transmission loss in the second case, we had the current in the second case too to be 566 amps. So if you do that substitution into this particular formula, once again you have our transmission losses on the second case to be 961070 RL. That's the power loss. So watts. Okay, it's in watts. Okay, and this one too is in watts. Okay, so take note of that. So now the question says that we should compare the two values. Okay, we should compare the two values. So say that how do these losses compare in the two cases? So let's see the percentage in reduction if you improve the power factor, because you can see clearly that in the first case we had a higher losses than in the second case. So let's see the percentage in reduction when the power factor was improved. So since we know that the power loss of the second one is less than the first one, we can make this an analysis. So the percentage reduction will be the power loss 2 minus power loss 1 over power loss 1. Okay, so if you do that substitution, you can see that the RL and the RL will cancel. So you take your calculator and make this substitution, and you see that we get 28% reduction. Okay, so that is it. So since we notice that transmission power losses are 28 less in the second case, while the real power supply to the load is the same. So you can see that at the same real power supply, the losses in the second one was 28% less than the losses in the first one. So operating at an improved power factor will reduce the power losses on the transmission line. That's why every company always wishes to operate at a proper or a correct power factor. So that is it for the question. Okay, so let's see. So we are saying that the ability to adjust the power factor of one or more loads in the power system can significantly affect the efficiency of the power system. So the lower the power factor, the greater the losses, as we saw in the other one. So we were having a power factor lagging, and with that one, we had a higher losses in the power system. So since most loads in the power system are induction motors, so we can't adjust induction motor the full excitation or the power factor of induction motor. So to improve the power factor of the entire system, is good for us to connect one or more over excited synchronous motors, or synchronous motor to operate in a leading power factor, so that we'll be able to improve the power factor. That's why we always advise that we use a synchronous motor in an industry. Okay, though synchronous motor has its advantages and disadvantages, because you can't adjust the speed easily with a synchronous motor, but it's always advisable to use a synchronous motor for the purpose of power factor corrections. So these are the following reasons why you need to connect a synchronous motor to the power system. So the first one is a leading load supplies some reactive power to a lagging load in the system. Since this reactive power does not travel along the transmission line current is reduced, reducing the power losses. Okay, so it's just a matter of, instead of you to transmit reactive power through the power lines to the load center, this time around we say that we don't transmit the reactive power, but rather we generate the reactive power at the load side. Okay, we generate the reactive power at the industry, so that the only thing that will be transmitted will be only the real power. In that case, we'll be able to reduce the current, the line current. Reducing line current means that reducing the power losses on the transmission line. It's just like you want to let's say undertake a project in maybe a particular town, okay, and you are a contractor. So you go with the skilled labor and then the unskilled labor. Okay, so if you are to go with the skilled labor and unskilled labor, the cost for transportation become higher. Okay, what about for the unskilled labor? You can get them anywhere. So it's just a matter of, okay, fine, I'm the contractor. Why don't I transport only the skilled labor, so that where I am going to have my project, I will just employ unskilled labor over there. In that case, I'll be able to reduce my cost of transportation, the cost of transporting the unskilled labor from maybe my country to the site. Okay, I hope you get a scenario. Instead of transmitting both the skilled and the unskilled labor from my country to where I'm going to have the project, I will say that, okay, this time around I am going to transport only the skilled labor, so that where I'm going to have my project, I'll just employ unskilled labor over there. Here we are going to generate the reactive power at our load center. So the only thing that will be transmitted will be only the real power. So in that case, you minimize losses. Okay, so another case or reason is, since the transmission line carries less current, the line can be smaller for a given power flow, reducing the system cost. Okay, just as I just explained. Okay, so this time around, since I am going to transmit or transport only the skilled labor, in that case, if at first I needed maybe 5 buses to transmit both the skilled and the unskilled labor, this time since I'm transmitting only the skilled labor, I will need maybe 1 or 2 buses. In that case, I've reduced the number of buses. Here, since we are transmitting only the raw power but not reactive power, or a small of reactive power, we'll be able to what, minimize the size of our cables, our transmission lines, thereby reducing what, the system cost. Go higher or larger lines comes with what, a cost. Another point is the overexcited mode of synchronous motor increases the power or the motor maximum torque. We discussed all these things in our previous lecture. So that is one reason why, or reasons why we always have to connect a synchronous motor to our power system for power factor improvement. So usage of synchronous motor or other equipments increase the overall power factor is called power factor correction. So connecting synchronous motor to improve the power factor is called power factor correction. Since a synchronous motor can provide power factor correction, many loads that can accept constant speed are driven by over-excited synchronous motor. All right. So there are other methods that we can improve power factor. Okay, but for the sake of this course, we are only focusing on synchronous motors. Okay. So when we get to maybe power system operation and control, we will look at the other methods that we can use to improve power factor. Okay. So this is the end of today's lecture. Until we meet again, in our next lecture, we will look at starting of synchronous motors. So you can read on that till we meet again. So this is Akinele Bismarck. I wish you good luck in all your endeavors. Goodbye.